Welcome to the course on discrete structures in computer science. The first topic we shall discuss deals with sets. Sets are the most elementary building blocks of much of math, including the type of math that will be the subject of this course. Much of this might be familiar to you, but let us go through the material anyway, so we get on the same page with respect to concepts, notation, and terminology. We begin by reviewing some of the very fundamental aspects of mathematical sets. Basically, sets are collections of stuff. They can contain all kinds of things. Numbers are common, strings are the sets. They're not limited to containing only one kind of object, even though they often do. Sets can also contain different numbers of things, some even infinitely many different things. For example, the set of natural numbers, represented by this bold n. During this course, we adopt the convention that the natural numbers start with 0. If we want to talk about the positive natural numbers without 0, we put a little plus sign in the exponent of the n. The set that contains nothing is called the empty set, and it is written by a 0 with a slash through it. There's only one empty set, which means it makes no difference what is not in it. If it is empty, it's the empty set. The things in a set are called its elements. The key here is that for any set and any mathematical object, the object either is or is not an element of the set. For example, 3 is an element of 1, 2, 3, 4. 11 is not an element of 1, 2, 3, 4. And the set containing only 3 is not an element of 1, 2, 3, 4. With that, what about those two statements? 0.9 repeating, is that an element of 1, 2, 3, 4? And is the set containing 2, 1 an element of the set containing 1, 2 and the set containing 3, 4? By the way, during these videos, I shall occasionally ask these kinds of questions and then pause a short moment at the stopwatch. This gives you the opportunity to pause the video and think about your answer to the question if you like, and then continue to see whether it agrees with the one that will then be given. The first statement is true, because 0.9 repeating is the same number as 1, or in other words, it's just a different way of writing 1. By the way, not everybody agrees with this right away, so if you have your doubts whether this is actually true, you can find material linked from the course page to clarify this a little. The second statement is also true, because the set consisting of 1 and 2 is the same as that consisting of 2 and 1. The learning here is that in order to determine whether a given thing is an element of a set, we need to be able to compare it with the elements we know in order to determine whether it is equal to one of them. In other words, the elementhood of a set is based on a concept of equality. The second example involves determining the equality of two sets. And between sets, equality is defined based on the elements they contain, also called their extensions. That's just a fancy word for the stuff in a set. Two sets are considered equal exactly if they contain the same elements. We say if they have the same extensions. This means that it doesn't matter which order we list the elements of a set in, or even whether we list some of them more than once. Remember that an object either is or is not in a set, and that's all there is to it. For two sets to be equal, they need to contain exactly the same elements. If one contains just one element that the other doesn't, they're different, not equal sets. And a bit of terminology, sets that contain exactly one element are called singletons or singleton sets. They are different from the element they contain. So 11 isn't the same as the set containing 11. The number of elements in a set is called its cardinality. We'll denote the cardinality of a set by using the number sign, but many authors use a pair of vertical bars to mean the same thing, a notation also used, for example, for the absolute value of a number. The cardinality of the empty set is 0, that of singleton set 1, and so forth. For now, we'll only consider the cardinality of finite sets, all of which are natural numbers. We shall look at infinite sets in some detail later in this course. Also note that we do not actually have a very precise definition yet of finite and infinite. That too will change. An important relationship between sets is that of inclusion. The idea is that all elements of one set are contained in another. We say that B includes A, or that A is included in B, or that A is a subset of B, or that B is a superset of A, if all elements of A are also elements of B. B may contain other elements in addition to those of A, or it may not. If it doesn't, it is of course equal to A. In fact, if A and B are the same set, if they're equal, then they are subsets of each other. Incidentally, the if with the two F's, that's not a typo, it's math speak for saying something like exactly when, or if and only if. And it means that the two statements connected by the if with the two F's are logically equivalent. So it's logically equivalent to say that A is a subset of B and B is a subset of A on the one hand, and to say that A and B are equal. Of course, that means that any set is always a subset of itself, and also that the empty set is a subset of every set. In this course, we use the subset sign without the lower bar to mean strict or proper inclusion, meaning that the two sets are not equal. We then also say that A is a proper or strict subset of B, or that B is a proper or strict superset of A. This is analogous to less than versus less than or equal to among numbers, for example. Just be aware, however, that other authors sometimes use the sign without the bar to mean regular non-strict set inclusion. We won't do it in this course, but it does happen in the literature. Let us look at some of the properties of set inclusion. The first is that it is transitive, meaning that if A is a subset of B and B is a subset of C, then A is also a subset of C. For example, 235 is a subset of 2345, which is a subset of n. Therefore, 235 is a subset of n, the natural numbers. Also, set inclusion is partial. This means that for any two sets, it may be the case that neither is a subset of the other. Here, the analogy to less than or equal to between numbers breaks a little, because for any two real numbers, for example, one is always less than or equal to the other. Can you come up with an example of two sets that are not related to each other by inclusion? This is an example of two sets that do not include each other, even though they have an element in common. 3 in this case. So in this segment we discussed sets and their elements, cardinality as a measure of the number of elements in a set, the relation between elementhood and equality, and inclusion in subsets. The next segment is going to be about defining sets and some operations on them.